Hello, I am Joe, and I'm speaking for Team 4 of the Senior Design Project. Our project is the Battery Diagnostic and Prognostic Tool application. We will be talking about these things in the presentation, including problem description, marketability, problem statement and objectives, intended users and uses, background, intellectual property, ethical considerations, concept development, and a conclusion. So our problem statement is that lithium batteries are being used in more and more things, and while they are very efficient, they are also dependent on ensuring that the wear and tear of time and usage doesn't get too bad. And so our project utilizes a battery management system in order to ensure that it is the most efficient and safe usage of the battery possible, both to ensure overcharging, overheating, undercharging, and other such wear and tear. Now, what sets our battery system apart is that we will be utilizing machine learning and AI solutions in order to both predict and diagnose problems before they even happen, and then recommend solutions to solve these problems, ensuring the most robust and efficient battery life possible. Now, in our marketability research, we found two Kickstarters that share similar uh, issues to our project. The first one, the Solar BMS and Digital MMP TV for PV for electricity and heating. This utilizes a BMS system for lithium batteries that will ensure better charging and keep them from overcharging or overheating for a longer lifespan. Similar for the second product, the Bacha and Batman Smart Charger and Battery, which is again utilized for batteries to ensure that they have a BMS system for smarter charging and smarter diagnostics. What sets ours apart, however, is the machine learning and AI, which these already have attained much support, the first one getting over $100,000 on Kickstarter. And so the marketability for our project is very large and very applicable in many industries. So our problem statement is that as these batteries become more into usage, how can we ensure that they're the most efficient and most safely used as possible? And our solution is the utilizing of AI and machine learning to ensure that the batteries are as efficient and robust as possible without any issues. So our objectives are developing a machine learning model that is capable of handling the data and then accurately predicting the battery's usage based on numerous trials and data. Um, Ensuring a proper communication between the components of the battery system so that data can then be analyzed and collected during its lifetime. Ensuring communication with a cloud server so that it can be both run locally and on the cloud, and then ensuring a user interface so that the program can be interfaced with by users to then see the data and interact with it. I will now turn this over to my teammate to talk about intended users. Thank you.
Hello, my name is Catherine Gonzalez, and I will be presenting the intended users, use cases, and background behind our project. Let's begin with who this tool is designed for. Our intended users include battery engineers, especially those working on in electric vehicle design and testing, grid storage operator managing large-scale battery banks for solar and wind system energy, research and development teams focus on battery health monitoring, performance improvement, and failure prediction. And also battery management systems or BMS developers who are integrating smarter AI-driven monitoring into their systems. All of these users share a common challenge, predicting when a battery will fail and why it's operating before it becomes a problem. That's where our project comes in. The core uses of our projects are to predict remaining useful life of a battery using advanced machine learning techniques, to diagnose early stage battery faults like capacity loss, internal resistance growth, or thermal anomalies, to help schedule preventive maintenance by providing insights into battery health trends, and potentially to use reinforcement learning for optimizing battery charging and discharging patterns over time. For instance, the NASA Battery Prognostic Benchmark tool is a great resource, but it's limited to raw datasets. There's no interactive system built-in diagnostic capability. Our tool takes things a step further by offering live diagnostic feedback and predictive functionality. Then there's also the CALSI Prognostic Toolkit from the University of Maryland. It's robust and academically proven, but also complex and hard to use for smaller companies or developers. In contrast, we are designing our tool to be user-friendly, modular, and easy to adapt to different use cases. We also reviewed their system, the Oxford Battery Degradation Dataset Framework, where we just mentioned that as a reference. Here you can see a clear breakdown of our project compares. Unlike other projects, our is built to support real-time diagnostic, predictive machine learning model integration, a clean, intuitive interface, and support for future expansion using reinforcement learning. We believe this combination of practical features and advanced analytics make our project not only innovative but also useful by engineers and operators in the field. Thank you, and I will pass to the next presenter.
Now, speaking of intellectual property, this application tool can be used with various brand of batteries in a variety type of uses, like EV charging or charging batteries in a solar home, or any type of uses that involve the charging of batteries. Now, this application tool also can be used in various type of computing platform, even in a mobile computing platform. However, this application tool must be protected by copyright, and the protections are for the application itself, the source code, the design of the graphic user interface, and the functionality of the application itself, which may involve any type of machine learning for reporting the state of charge, which is a diagnostic, and the state of health, which is a type of prognostic for the batteries to the user. And such application must be protected by copyright. Thank you.
My name is Jorge Rosquete, and I will be presenting on the ethical considerations and concept development of our project. Let's begin with the ethical foundation, as you can see here in the slide, for our project. Because we're dealing with sensitive battery performance data, we prioritize data privacy and security. Our system uses encryption and follows up GDPR compliant practices to protect information during cloud transmission. We also took care to avoid algorithmic bias. Our machine learning models are chosen for their transparency and interpretability, ensuring users can trust the diagnosis, results, and understand how the system makes its predictions. Another major consideration is accessibility. We've designed the interface to be user-friendly for both engineers and general mechanics, making sure it's intuitive without sacrificing technical depth. Lastly, our solution supports sustainability by helping extend battery life through predictive maintenance. This reduces electronic waste and promotes smarter energy usage, especially in industry like electric vehicles and renewable storage systems. For the concept development, now we explore 3 technical pathways to power the machine learning component of our tool. Option 1 uses XGBoost combined with a Flask interface and AWS cloud services. This combination offers high accuracy, fast training, and the flexibility to scale across both local and remote deployments. Option 2 pairs K-mean clustering with Streamlit and Google Cloud. While this setup is simpler and easier to implement, it lacks the predictive precision needed for detailed battery diagnosis. Okay. Option 3 involves a neural network model, Flask and Microsoft Azure. It offers strong predictive capabilities but comes at the cost of high complexity, resource demand, and limited efficiency for real-time edge processing. We evaluated all these 3 options based on accuracy, scalability, and system complexity. As you can see on slide number on concept development part 2, after a careful comparison, we selected option 1, which is the XGBoost plus Flash Pro AWS. Why? Because XGBoost is known for delivering superior predictive accuracy while being computationally efficient, which makes it perfect for environments like embedded systems or remote BMS setups. It handles large battery datasets better than traditional models like random forest, and it doesn't require the heavy computational load of neural networks. This solution supports offline operation, cloud integration, and low latency response, all key for the real-time diagnosis. It also aligns best with our team technical skill set and the timeline we're working with. As you can see on the comparison chart, I'm gonna rewind a little bit. As you can see on the comparison chart down here, XGBoost stands out for its accuracy and scalability while maintaining a lower complexity score than the other options. This makes it more balanced and practical choice for deployment and reliable battery health monitoring solution. Thank you.
In conclusion, our project seeks to create a better and more efficient battery management system for lithium batteries so that then they can unleash their full potential and be properly and safely and efficiently used in a broad range of applications, and hopefully allow these applications to be more wide-ranged and more strenuous than before, thanks to our system, which should ensure battery health, safety, and efficiency throughout an entire lifetime, hopefully strengthening it and lasting a longer life. Thank you.